Okay, so we're going to then first now look at the buck converter and derive the transfer functions like I mentioned in the beginning. Then we're going to look at the buck converter with the parasitics, and then we're going to look at the boost converter and the boost converter with parasitics, and then the buck boost and the parasitics. So the first stage is the buck converter. So the buck converter is, here's your DC input, the VG, and we're going to have a switch for right now. Of course, it's going to be an ideal switch because that's no parasitics, and then we'll add the parasitics later. There's a diode. We're going to have an inductor, a capacitor, and a resistor, R, and the output voltage is going to be V. And this is going to be a ground. Now, if we look at this, the switch, this is the switch, it's either going to be on or off. Therefore, this node here is going to be either V sub G or it's going to be 0, treating the ideal diode as 0 voltage. So this is going to look like a square wave. Beginning with 0, and when it switches on, it's going to go to VG. So as you can see, this period is that dt, and that period is the d prime t, just like we mentioned before, and this is the total time t. Sometimes I make t sub s, meaning the switching period. So I'll interchange t and t sub s. So t, and sometimes I'll use t sub s, which means switching period. So this diode later, we're going to have a drop on this. Now, how do you determine the drops? First of all, the power comes from this input. So when the switch is on, that's the direction, and therefore that's the direction of the current I. Now, when the switch is off, the inductor current will continue the current in the same direction, which means it'll turn on that diode. So that's how you determine the direction. The direction is plus minus, the direction here is plus minus, the direction here is plus minus, and the diode, when it turns on, it's going to be plus minus. Okay? So what we're going to look at is you're going to determine what is the voltage across the inductor. That will be the voltage VL. So if we make a little chart here and we say, okay, during the time the diode, the switch is on, which is dt, we're going to have the voltage across the inductor as being VG minus V. And when the switch is off, we're going to have a that's the d prime t period. We're going to have the voltage across that inductor to be V. Okay? And you can see that this is 0, and it's going to be V, meaning the minus direction. So in reality, it's minus V, but it's below the axis. So if you're looking at now, if we stick a current probe in this inductor, we're going to see that it's going to come up, ramp up the inductor current, and this is I in the inductor. Sometimes I'll use I sub L, sometimes I'll just use I. And then when it's off, it ramps back down. And this is during, again, the same time dt, and this is the time t prime t. This is going to be known here as the ripple. I like to define the ripple voltage as the peak to peak. Okay? So the average of this current is going to be I, which is the DC current that's going to flow. And that DC is the current that flows to the output. And that DC current, you know it's going to be DC because the output voltage is constant. That's what we want to make it, is to be constant. And therefore, it's a constant voltage divided by a resistance gives you a constant current. The control is D. That's the control. That's how we control the amount of output voltage for the duty cycle, just like we had before, that the output voltage is going to be derived as D times the input voltage V sub G. But we're going to prove that here. So again, this time can either be T or T sub S, but again, we'll just say T since we'll be consistent here. So let's look at this time here. We notice that if it's in steady state, which means we start at I at T0 and we end at I at the end of T. So we're coming up and coming down. Steady state means that this current will be the same as the initial current. This current, the final current, will be the same as the initial current. That will be in a steady state condition. And that's what we're looking to derive the output voltage for a steady state condition. So you will see that this is nothing more than a volt-second balance. The volt, this voltage, times the seconds should be equal to this voltage times the seconds. And that's what we mean by a volt-second balance. Now, that is nothing more than Faraday's law. If you look at L di dt as equal to V, and by the way, V is the average voltage, okay? So that we can relate L di is equal to V dt. So we are going to integrate that from I of 0 to I of t, the whole period. That means that for each interval from V, this V, this is not the V output, so I should say this is the VL, the inductor voltage. That means that this V during the T on time is going to be Vg minus V. And for the off time, or d prime t time, it's going to be V. So we are going, in either case, it's still a DC, so we can pull that out of the integral, and this is going to go from 0 to t, but we have to separate these. So let's get to the next section. And what we have now is L I of 0 to I of t dt, and that's nothing more than L I of t minus I of 0. And notice that if I of t is equal to I of 0, then this is 0. So that's the steady state condition. But that's equal to the voltage VL, but now we have to split. We have to find VL from 0 to T on dt plus another VL, so I'm going to call this 1 and VL2 from T on to T dt. So if we look at that, that is just 0 is equal to VL1, that's just for the time on, which of course we made it T on. And that's going to be T on. Plus, we could see this is VL2, which is going to be T minus T on. Okay? Hence the name volt second, volt second, volt second balance. So we just plug in what this is from the beginning chart. It was VL1 is just VG minus V times T on, plus the VL2 was a minus V T minus T on. So now all we have to do is solve for V out over Vn. Now we can divide both sides by T. That means everything is divided by T. So we notice that 0 over T is still 0, and this becomes Vg minus V, and this becomes T on D. That's T on over T. Plus, there's a minus here, so a plus times a minus is a minus V, and this portion now is now D prime. So simply put now, we have 0 is equal to just multiply out dV sub G minus dV minus a V D prime. So we could see that this is dVg, and we got a common V, so we have a minus V times D plus D prime. And if you remember, D prime is equal to 1 minus D, then we note that D plus D prime is D plus 1 minus D, which is equal to 1. So always remember that D plus D prime is always equal to 1, which makes sense. So now we come back to this equation, and we have 1 here, and therefore we have 0 is equal to dV sub G minus V, and we have our transfer function, which means that V over V sub G is equal to D. And that's what I promised you, that it was a buck converter is V over V sub G is equal to the duty cycle. So now we're going to consider the buck converter with parasitics. Remember, we have no parasitics in the first one. That's why V over Vc is equal to duty cycle. So now let's look at the same converter, the buck converter, with parasitics. So here's the buck with parasitics. Okay, so the parasitics we're going to look at first here. You're going to see that this is the Vg. Sometimes I'll draw a circle and put a plus minus. Sometimes I'll just draw a DC voltage. And we'll look at the switch effect with the control element D. And now we'll notice that this voltage is going to have an RDS on. That's the on resistance of the FET when the FET is going to be turned on. Of course, when the FET is off, it's going to be an open. We have the diode, which is going to be construed as VD, the diode drop. As we know the direction of the current from the source, we know it's this direction, and that's the VL. And we have a capacitor, and we're going to include the ESR in the capacitor. ESR. And here's our load resistor, R, sometimes RL. We have a plus minus. And here's our ground. So now we have all the elements, and we're going to have an R winding resistor. That's the resistance of the inductor. Okay, so now we have, so what parasitics do we have? We have the RDS on, we have the RW winding resistance of the inductor, and we have the series resistance of the capacitor, C. Okay, so when the switch is on, we're going to have two circuits. This is going to be for T on, and what's going to happen is this is going to be replaced by a VG with a resistor of RDS on. Again, the current's going to flow It's going to produce a plus minus. The diode is going to be open, so that's the open. Then we have an inductor, V sub L, whose current is I, and we have a winding resistor, RW, the capacitor, ESR, and we have a resistor load. That is one section. Then what we're going to have for T minus T on, which is the D prime T period, and this is going to be the DT period. We have the switches open. So we're going to have V sub G here with the switch being open and the diode being on. So again, for the diode, that's going to be the diode drop, because we're not going to be talking about ideal. We're going to have the V sub L. We're going to keep the polarity the same, never change the polarity. We're going to have RW. We're going to have the ESR, the cap. And we're going to have V. And this is R, that's the ESR, and that's the C. Okay? We still have the same current flow, same direction. Don't change the direction, please. And don't change the direction of the polarity. So you see we have two circuits. So looking at this circuit, we have an LDIDT. And what is that? That's really the voltage across the inductor during the T on period. And you're going to see that what is that equal to? Well, simply put, to collect terms, what is this voltage across this inductor right here? That is equal to VG minus the current flows. It flows through here too, I, and that's going to be I times RDS on minus I times RW minus V. Okay? This is going to be for the time on period. What is it going to be for this circuit here? Well, this is going to be equal to, again, LDIDT. That's V of L. It's going to be equal to minus VD minus IRW minus V. As we could see, we could do our little plot again. And you could kind of see what this looks like. This is going to be the time on here. And that's DT. And this is going to be then D prime T, which is the time off. So it's going to repeat. So that voltage here is nothing more than this voltage here. And this voltage here is nothing more than this voltage here. Okay? So we could see that by Faraday's law, we're going to do a volt-second balance again. And all we do here for the volt-second balance is to say, okay, the volt-second balance says Faraday's law at the end. Remember, the I of 0 is going to equal to the I of t. That means that we're in steady state. Okay? If it's not, you just wait until it becomes steady state. I mean, that's the idea. You want a steady state. In steady state, you want to know what your output to input transfer function is with parasitics. So we see that we're going to have D, just like we had before, the time on over the T. Now I'm going to just write D. VG minus IRDS on minus IRW minus V plus a D prime times what? A minus VD minus IRW minus V, and that's equal to 0. In my book, I go through all the steps. It's just algebra from here, but in my book, I go through step by step. And the conclusion is I'm trying to find V to V sub G, the transfer function. So that's going to be equal to D after you solve for the terms. And that is going to be D times this expression. When you solve it, again, the details are all in my book, D over D prime over D, sorry. VD, the diode voltage, over V sub G. And divided by 1 plus D R ds on plus RW over R. And this is what this expression is going to be. So what is this here? What is all this? That is the efficiency. Because ideally, remember no parasitics, V out over V in was D. But now we have this term here, which is the loss term. Think about this. If this were ideal, if the RDS on was 0, this term would be 0. And if the RW winding resistance would be no winding resistance, that would be 0. So this bottom would be 0 and this would be 1. In the top part, if the diode voltage was 0, an ideal diode, then this term here is 0. And you'd have 1 over 1, 1 over 1, which is then output over input would be equal to D. So this term is our efficiency, and therefore output over V sub G, as I promised, is equal to D times efficiency, or efficiency times D, either way. Okay? Now, what if we come back to our equation, our circuit, okay, and we want to add in our circuit, instead of a Zener diode, we want to also add the Zener resistance of that diode. Remember what the circuit looks like. All now is, instead of a diode before, we're going to appraise the parasitic. We're going to add another parasitic, and that's the series resistance of the diode. Oh my goodness, do you have to start all over again? No, you really don't. Because all you observed, if you observe that during the time on, you see the on resistance, RDS on. And that's where this came in, is D RDS on. Because it's seen, when the switch is on, that's the only time it sees the on resistance. Now, look at RW. Well, RW in the circuit sees both when it's D or D on, or D prime. It sees the same for both cycles because it's in series with the inductor. Therefore, there is no D on D prime. So for this switch, notice that this diode only turns on during the time D prime. So all we have to do to modify the equation is V over V sub G is D times this is 1 minus D over D prime. D prime over D. VD over V sub G divided by now 1 plus D RDS on plus RW plus what? D prime, because that's when it sees RZ, divided by R. And there you go. Very simple change to add on to this. And now our efficiency again, this will become our new efficiency. And V out over V G, or V over V sub G, which is V out, is D times the efficiency.